Chapter 9.1, Exploring Rational Functions Using Transformations. A rational function takes the form f of x equals p of x divided by q of x, where both p of x and q of x are polynomials, and q of x is not equal to 0. The following are all examples of rational functions. F of x equals 4 divided by x, f of x equals 5 divided by 3 times x minus 4, and f of x equals 2x squared plus 7x plus 3 divided by x squared minus 9. Use the table of values below to sketch the graph of y equals 1 over x. When x equals negative 10, 1 divided by negative 10 is negative 0.1. When x is negative 1, 1 divided by negative 1 is negative 1. When x is negative 0.01, 1 divided by negative 0.01 gives us 100. And when x equals to 0, we can't divide by 0. 1 divided by 0 gives us an error, so that is undefined. When x equals to 0.01, 1 divided by 0.01 is 100. When x is 1, 1 divided by 1 is 1. And when x is 10, 1 divided by 10 is 0.1. Let's plot these points. When x equals negative 10, y is negative 0.1. So just barely below the x-axis. When x is negative 1, y is also negative 1. And then when x is negative 0.01, so really close to x equals 0 to the y-axis, but just on the left-hand side, then our y value is, this should be negative 100, sorry. So our y value is getting very, very small. So we end up with a piece of the graph that looks something like this. And then on the positive side, when x equals to 0.01, so just to the right of 0, then y equals 100. So again, we have, as x is close to 0 on the positive side, our y values are getting very, very large. Then x equals 1, y equals 1, and x equals 10, y equals 0.1, so just above the x-axis there. So we get the piece of the graph that looks similar to the first piece, just in quadrant 1. Equations of asymptotes. Asymptotes are a line that a graph approaches but does not touch, doesn't actually ever equal that value. It's never going to intersect with that line. So we have a vertical asymptote, which is the y-axis. So x equals to 0. We also have a horizontal asymptote. Our two sides of the graph approach the x-axis, but they never actually touch the x-axis. So we have a horizontal asymptote at the x-axis, which is at y equals to 0. The domain for the base rational function 1 over x, if we look at our graph, we see that all values to the left of x equals 0 are part of our graph, and all values to the right of x equals 0 are part of our graph. But we know that x equals to 0 is not part of our graph. We can see this by looking at the table of values. We know that at x equals to 0, the function is undefined. We can also see this from our asymptotes because x equals to 0 is our vertical asymptote. So our domain is x such that x is all the real numbers except x cannot equal to 0. Similarly, for the range, if we look at the graph, all the values below y equals to 0 are part of this function y equals 1 over x, and all the values above y equals to 0 are part of the function. The only value that's not part of the function is y equals to 0. So y such that y cannot equal to 0. So all the real numbers except for 0 are part of the range. If we look at the denominator of our function, non-permissible values are the values that make the denominator equal to 0. In this case, that would be x equals to 0. So x cannot equal 0, or you could say x equals 0 is a non-permissible value. Note, the function is undefined when x equals 0. This is called a non-permissible value in PV. Rational functions may have vertical and horizontal asymptotes. We saw that. Y equals a divided by x, or y equals a times 1 over x, will have asymptotes at x equals to 0 and y equals to 0, and a is our vertical stretch factor. Y equals to a divided by x minus h plus k has a vertical asymptote at x equals to h, which is also the NPV, and a horizontal asymptote at y equals to k. So if we have our function written in the form where we can see the transformations, then we can tell what our vertical and horizontal asymptotes are, because the vertical asymptote is the h value and the horizontal asymptote is the k value. A transformation is applied to f of x equals 1 over x, so it has a vertical stretch factor of 4 about the x-axis, is reflected about the x-axis, translated 3 units right and 5 units down. The new equation in the form y equals a x minus h plus k is, so we have a vertical stretch factor of 4, that means a equals 4. It's reflected about the x-axis, so a is negative. Translated 3 units right, h equals 3, and 5 units down, k equals negative 5. So we get y equals negative 4 over x minus 3, and then minus 5 outside the rational. The equations of the asymptotes, we just saw that when it's in this form, y equals a over x minus h plus k, it has a vertical asymptote at x equals to h. So our vertical asymptote is at x equals 3, and it will have a horizontal asymptote at y equals to k, which is negative 5. Our domain then would be x such that x is all real numbers except x cannot be 3. And our range would be y such that y is all real numbers except y cannot be negative 5. If we were to do a quick sketch of this, our vertical asymptote is at x equals to 3. Let's say that's here. And our horizontal asymptote is at y equals to negative 5. It's reflected in the x-axis because our a value is negative. So instead of having the point up here that's in quadrant 1, that's going to be reflected down into quadrant 4. And this part that was in quadrant 3 is going to be reflected up into quadrant 2. And then it shifted down and over to the vertical and horizontal asymptotes. So it'll look something like this. There's a quick sketch of our function. Without using your calculator, state the transformations that occurred to y equals 3 divided by x minus 3 plus 2. We have an a value equal to 3. Our h is equal to 3 as well, because we have x minus 3. And then our k is equal to 2. So that results in a vertical stretch factor of 3 about the x-axis. We have a horizontal translation or a shift of 3 units right. And we have a vertical translation or shift 2 units up. Equations of the asymptotes. Our vertical asymptote is x equals the h value. So x equals 3. And our horizontal asymptote is y equals the k value, y equals 2 in this case. Determine the x and y intercepts. For the x-intercept, y is equal to 0. So in the x-intercept, sub y equals 0 in. We get 0 equals 3 over x minus 3 plus 2. Subtract 2 from both sides. Negative 2 equals 3 over x minus 3. Multiply both sides by x minus 3. We get negative 2 times x minus 3 equals 3. Multiply this negative 2 in to the brackets. Negative 2x plus 6 equals 3. Subtract 6 from both sides. Negative 2x equals negative 3. And then divide by negative 2. We get x equals positive 3 over 2, or 1.5. For the y-intercept, x is equal to 0. So sub in x equals 0. We have y equals 3 over 0 minus 3 plus 2. Y equals 3 over negative 3 plus 2. Y equals negative 1 plus 2. Y equals positive 1. Let's graph our rational function without using our calculator. We have a vertical asymptote at x equals 3. And a horizontal asymptote at y equals 2. If we look back at our first rational function, when we graphed to the base rational function y equals 1 over x, we see that we have our asymptotes that cut our grid into 4. In this case, the 4 quadrants because they're at x equals 0, y equals 0. And then we have 2 curves, one in the top right of our asymptotes and one in the bottom left of our asymptotes. So we're going to have a similar situation. We're going to have two curves, and since there was no reflection in our transformations, we didn't have a reflection across the x-axis or the y-axis, so our two curves are also going to be in the top right and in the bottom left. So let's plot some points to figure out where they're going to go. We have that the x-intercept is 1.5, plot that, and the y-intercept is at 1. We can also use mapping notation to determine some other values. So if we look back at our y equals 1 over x, we have a point here that is 1, 1. And we can use mapping notation to transform that point for our function. X, y goes to, our x is affected by a horizontal shift right 3, so x plus 3, and our y has a stretch of 3, so 3y, and then shift up 2 plus 2. If we put in the point 1, 1 to our mapping notation, we get 1 plus 3, and then 3 times 1 plus 2, which gives us 4 and 5. So 0.45 is on the function. And then we could do the point negative 1, negative 1, which was on our function, on our original function here. Let's transform that point using mapping notation. Negative 1, negative 1. Negative 1 plus 3. 3 times negative 1 plus 2. We get 2, and negative 3 plus 2 is negative 1. X equals 2, y equals negative 1. That gives us a pretty good idea of what the curve's going to look like on the bottom left. We know that it's going to get close to the horizontal asymptote. It's going to come and curve through those points, and then it's going to get close to our vertical asymptote. To do the part in the top right now we only have 1 point. Now we could pick x values and sub them into our function, y equals 3 over x minus 3 plus 2, to find y values, but we can also use symmetry. When we have a rational function like this that has two curves, and those two curves are on opposite sides of the horizontal asymptote. So here's our horizontal asymptote. One curve is below that and one curve is above that. When we have that situation, then there's symmetry across a diagonal line that goes through the intersection of the two asymptotes. So in this case, because of the way they're set up, that line of symmetry would be here. Okay, so if we look at the points that we have in the bottom left, I'm just going to draw my line of symmetry. If I look at the points that are down here in the bottom left, I can count how far away they are from the line of symmetry, and then count that far away on the opposite side, and those points would be there. If I look at this point, it is 1, 2 below the line of symmetry. So if I go 1, 2 above the line of symmetry, I get a point, and that one we already had. It's a little harder with points that are in the center, so I'll start by looking at this point here. So it is 1, 2 below the line of symmetry. So if I go 1, 2 above the line of symmetry, I'm going to put a dot right there at x equals to 6 and y equals to 3. Then for this dot, it's a little bit harder, but I can think about the symmetry in a different way. If we look at this point here, from the center of the two asymptotes, we would have to go 3 left and one down. So -3 in the x direction and then -1 in the y direction. When we look at the point that it's symmetrical with, we go up 3 and right 1. So +3 in the y direction and then +1 in the x direction. So what we notice is that the x and y values switched, and also the signs or the directions switched. So this dot here that we haven't placed the symmetrical one yet, it is -1.5 in the x direction and -2 in the y direction. So it's going to be +2 in the x direction, because it was -2 in the y direction, and then it's going to be +1.5 in the y direction. So we're going to have a dot right there. Then we can draw the curve that's in the top right. So we get close to the vertical asymptote, we come down and go through these points, and then we get close to the horizontal asymptote. Describe the characteristics of each rational function in the table below. Y equals 3 over x. I don't know why that looks funky, but it should just be 3 over x, and this one should be y equals 4 over x plus 1, and then plus 5. Non-permissible values. So what makes the bottom equal to 0? Well, this one's just x on the bottom, so our non-permissible values would be x equals to 0. You can also write x not equal to 0. It doesn't really matter. Okay, we're just saying that those are the values for x that are not allowed. So whether you write it as the non-permissible value is x equals 0 or x cannot equal 0, I don't care. Non-permissible values for the next one, x plus 1 cannot equal to 0. So x cannot equal to -1. Or x equals -1 is our non-permissible value, either one. Let's skip the next two for a second. Let's drop down to our vertical and horizontal asymptotes. We know that our vertical asymptote is x equals to h, which in this case h is 0, so x equals to 0, x equals h, and then our horizontal asymptote is y equals to k, which is also 0 in this case, so y equals 0, y equals to k in general. For the second function, we have x plus 1, which means h is equal to -1, so our vertical asymptote is x equals to -1, and in general, x equals to h. Our horizontal asymptote is y equals to the k value, which is 5. Then let's do the domain and range. So starting on the left, domain is everything except that value from the vertical asymptote or from the NPV. So x such that x is all real numbers except x cannot equal to 0. Range, y such that y is all real numbers except for the value of the horizontal asymptote, so y cannot equal to 0. On the right hand side, domain, x such that x is all real numbers except x cannot equal to -1. Y such that y is all real numbers except that y cannot equal to 5. Now let's discuss the behavior near the NPV. I'm going to graph the function. Y equals clear, clear. We have 3 divided by x. Graph that. And here's what we get. Oftentimes when we graph rational functions, in the graph, it kind of looks like they're connected. So we see this red part here, right? We've got this part and we've got this part, but then we've also got the red line in the middle, which is showing us our vertical asymptote, but it kind of makes it look like the three parts are connected. They're not. So just keep that in mind when you graph a rational function using your graphing calculator. The two sections are not connected, okay? Even though it may look like it in the graphing calculator. All right, so behavior near the non-permissible value. The non-permissible value is what makes the denominator equal to 0, which we said was 0 for x. So as x is approaching 0 from the right, so follow my little dot. As x approaches 0 from the right, what's happening to the y values? Well, they're getting bigger and bigger and bigger and bigger and bigger. And they're going to keep getting bigger. Okay, so it's going to shoot up because remember, this piece here is going to approach the vertical asymptote, but it's never going to touch. So it's just going to keep going up and up and up and up and up and get closer and closer to x equals 0, but it's never going to get to x equals 0. So as x approaches 0 from the right side, our y value is approaching positive infinity in this case. And then if we look at the other side of the graph, as x is approaching 0 from the left side, our y values are getting smaller and smaller and smaller and smaller. So as x approaches 0 from the right, y approaches infinity, and as x approaches 0 from the left, y is going to get bigger and bigger in the negative direction. So y is going to approach negative infinity. Let's do the other function now. Back to y equals, clear that one, and enter this one. 4 divided by x plus 1, and then plus 5. And here's our graph. Again, the pieces are not connected. Even though it does draw the vertical asymptote, you have to remember that the pieces are not connected. As we approach the non-permissible value from the right-hand side, again, we're going higher and higher and higher with the y values, and they'll keep going higher. So as x approaches the non-permissible value, in this case was -1, from the right, y approaches positive infinity. And then as x approaches -1 from the left, y is getting smaller and smaller and smaller and smaller. And as x approaches -1 from the left, y approaches negative infinity. Now let's talk about the end behavior. So the difference between the behavior near the non-permissible values and the end behavior is talking about what is happening as the x values are approaching positive and negative infinity. Okay, so looking at our graph, we'll do the second one first since we already have it graphed. As x is getting bigger and bigger and bigger and bigger and bigger, our y value is going to get closer and closer to our horizontal asymptote, which in this case was y equals to 5. So we see here we have y equals 6.48. It's getting closer to 5. It's now 5.8, 5.7, 5.6, 5.5, 5.4, 5.3, and it's going to continue getting closer and closer to 5. So as x approaches infinity, y approaches 5. And then on the other side, as x approaches negative infinity, same thing, our function is getting closer and closer and closer to the horizontal asymptote, which is 5. And as x approaches negative infinity, y approaches 5. Looking at our other one here, so our horizontal asymptote was 0 in this case, so it would be the same end behavior as the one we just did, except instead of y approaching 5, it would be y approaching 0, because that is our horizontal asymptote. As x approaches infinity, y approaches 0, and as x approaches negative infinity, y approaches 0. Another way that we can write this is as the absolute value of x approaches infinity, which would include x approaching infinity and x approaching negative infinity, y approaches 0. Over here, we could write that as absolute value of x approaches infinity, y approaches 5. We can do the same thing for the behavior near the non-permissible values. Instead of saying as x approaches 0 from the left and as x approaches 0 from the right, we can say as x approaches 0, so from either direction, absolute value of y approaches infinity. So that means both y approaches infinity and y approaches negative infinity. And then over here, as x approaches -1 from either direction, absolute value of y approaches infinity. You will see a chart like this on your quiz and your test. So make sure that you understand how to describe the behavior near the non-permissible values and how to describe the end behavior. Change each equation into the form y equals a over x minus h plus k. Identify asymptotes and intercepts and sketch each graph. So in order to change the function into the transformation form, we're going to have to do long division with polynomials, which is something we haven't done before. There is a worksheet that you should have, if not it's on D2L, that goes more in depth on how to do this process. So definitely reference that worksheet. I'm going to go through it fairly quickly here. We're going to take x minus 4 and we are dividing 2x plus 2 by x minus 4. So this is how we set up our long division. Kind of looks like a square root sign, but it's not a square root sign. We want to know what we would have to multiply this variable by to get the first term underneath the division sign. So I would have to multiply x by 2 to get 2x, which means I put a 2 right here. Then I multiply this binomial by 2, and I put my answer down here. I get 2x minus 8. Then I subtract 2x minus 2x is 0, so that's gone. 2 minus -8 is 2 plus 8, which is 10. Which then gives me, I still have a remainder of 10. This is called the remainder. So I still have that 10 divided by x minus 4 because I couldn't fully divide, but then I have plus 2 because I was able to divide out 2. So now it is in the form a over x minus h plus k, and a equals 10, which means a vertical stretch factor of 10 about the x-axis, we have h equals 4, which is a horizontal translation for right. And we have k equals 2, which is a vertical translation to up. The h value also tells us that our vertical asymptote is at x equals 4, and the k value tells us that our horizontal asymptote is at y equals 2. Next part says equation of the asymptotes. What we just saw from h and k, our vertical asymptote is at x equals to 4, and our horizontal asymptote is at y equals to 2. The intercepts, for the x-intercept, we want to let y equal to 0, or sub in 0 for y. Let's plug that into our transform function. 0 equals 10 over x minus 4 plus 2. We're going to subtract 2 from both sides. Negative 2 equals 10 over x minus 4. We're going to multiply both sides by x minus 4. Negative 2 times x minus 4 equals 10. We're going to multiply that negative 2 into the brackets. Negative 2x plus 8 equals 10. We're going to subtract 8 from both sides. We get negative 2x equals 2. Divide by negative 2, we get x equals negative 1. Y-intercept, we're going to let x equal to 0, plug it in, y equals 10 divided by 0 minus 4 plus 2, y equals 10 over negative 4 plus 2, y equals 5 over negative 2 plus 2. 5 divided by 2 is 2.5, so y is negative 2.5 plus 2, which gives us y equals negative 0.5. Now we can graph our function. Starting with our asymptotes, we have a vertical asymptote at x equals to 4. And a horizontal asymptote at y equals to 2. Then we have our x-intercept at x equals to negative 1, and our y-intercept at negative 0.5. We can then use symmetry to plot these 2 points on our other curve. From the center of our asymptotes to get to the x-intercept, we have to go 1, 2, 3, 4, 5 in the negative x direction, and then 2 in the negative y direction. So that would change to 2 in the positive x direction and 5 in the positive y direction. So a point at 6, 7. For this point, from the center of our asymptotes, we're going 1, 2, 3, 4 in the negative x direction, and then 2.5 in the negative y direction. That would translate to 2.5 in the positive x direction and 4 in the positive y direction. So we would have a point at 6.5, 6. We could also calculate a few more points if we like. Let's plug in points for when x equals 8. We have 10 divided by bracket 8 minus 4, close bracket, plus 2, and we get 4.5. So at x equals to 8, y equals to 4.5. And then we could find the point that is symmetrical to that on the other side. to get to this point from the center of the asymptotes, we are going 2, 3, 4 in the positive x direction and 2.5 in the positive y direction. That would translate to 2.5 in the negative x direction and 4 in the negative y direction. So a point at 1.5 for x and -2 for y. For the top right part, it's going to look something like this. And then the bottom left part is going to look something like this. And there's the graph of our function. Graph the function f of x equals 1 over x squared on the first grid, using your graphing calculator to help you. Using your knowledge of transformations, graph g of x equals -1 over x minus 3 squared, and h of x equals 2 plus 5 over x squared plus 2x plus 1 on the other two grids. One divided by x squared graph. Notice that the rational functions that we graphed previously had linear relations on the bottom, and this one has a quadratic on the bottom. So we get this graph here. We still have our non-permissible value at x equals to 0, so we've still got an asymptote here, vertical asymptote at x equals to 0. And looking at our graph here, if I just go along this line, we have y equals getting really close to 0. And on this side, getting really close to 0, but staying above 0. So we have a horizontal asymptote at y equals to 0. And then we see that when x is equal to 1, second trace, we can do the value, number 1. When x is equal to 1, y is equal to 1, which makes sense. 1 divided by 1 squared would be 1. So I can plot a point at 1, 1. Also, when x is equal to -1, y would be equal to 1. So we have a point here. And then we can draw our function. So it's going to get really close to the vertical asymptote. It's going to come down and go through that point. It's going to get really close to the horizontal asymptote. And then same thing on the left side. It's going to get really close to that vertical asymptote. It's going to come down, go through this point, and then it's going to get really close to the horizontal asymptote. So using our knowledge of transformations, let's graph g of x equals -1 over x minus 3 squared. We have -1, so a equals -1. And then x minus 3 squared, h equals 3. So it's going to go to the right 3 units. And a being -1 shows a reflection across the x-axis. So instead of being up here in quadrants 1 and 2 like our first one, this one is going to be reflected down into quadrants 3 and 4 because a is -1. It's also going to be shifted 3 units to the right because h is 3. So our vertical asymptote is going to be at x equals to 3 instead of x equals 0. Horizontal asymptote hasn't moved. It's at y equals to 0. We're still going to have our point that was at 1, 1. It's just going to be reflected. So it would be reflected to be here at x equals 1, y equals -1, and then it's going to be shifted 3 to the right, so 1, 2, 3. So it's at x equals 4, y equals -1, x equals 4, y equals -1. And then same with the point that was on this side, the x equals -1, y equals 1. First it gets reflected across the x-axis to be at -1, -1. Then it gets shifted 3 units to the right, 1, 2, 3. So it lands at x equals 2, y equals -1. 2, -1. And then we can draw our graph. So we're getting close to our horizontal asymptote. Then we go through our point, then we're getting close to our vertical asymptote. Same thing on the other side, we're close to our horizontal asymptote. We go through this point, then we get close to our vertical asymptote. And there we go. Last graph, h of x equals 2 plus 5 divided by x squared plus 2x plus 1. Let's graph that using our knowledge of transformations. It doesn't quite look in the form we need it to be, but if I look at this function here, that is a perfect square trinomial, so I can factor that to a binomial squared. And it factors to x plus 1 squared, because x times x is x squared, x times 1 is 1x, 1 times x is 1x, that gives us 2x, and 1 times 1 is 1. So now it's in the form showing the transformations. So we have an a value of 5, we have a k value of 2, and we have an h value of -1. The h is also our vertical asymptote, and the k is our horizontal asymptote. We can draw those points. Vertical asymptote at -1. Horizontal asymptote at 2. We have the points on our original function, -1, 1, and the other point 1, 1. We can use mapping notation to plot those points on our transformed function. Mapping notation in general for this would be x, y goes to x minus 1, 5, y plus 2. If we plug in the point 1, 1, we get 1 minus 1, and then 5 times 1 plus 2, which gives us 0 and 7. Plot that point on there. And the next one, -1, 1. We get -1 minus 1, and 5 times 1 plus 2, which gives us -2 and 7. -2 and 7. We could use our calculator to find a couple points for certain x values. So let's go back to our regular screen here. Let's just plug in if x is equal to 2. We have the fraction 5 divided by bracket x, which is 2 plus 1, close bracket, squared, close the other bracket to end my fraction, and then plus 2, which gives me 2.555. So at x equals to 2, y is about 2.5, which means I expect that when x equals to -4, we would have a y value that's the same. So let's try it out. I'm going to go back up to my equation, hit enter so that I can change it. I'm going to just change my x value to a -4 and hit enter, and we get 2.555. Okay, so now we can graph our function. We know that it's going to get close to our vertical asymptote. It's going to come down and curve go through our 2 points, and then get close to our horizontal asymptote. Same thing on the other side. It's getting close to our vertical asymptote. It's going through our points, curving, and getting close to the horizontal asymptote. And there's our rational function. And lastly, let's write the domain and range for each of our functions. Starting with f of x, looking at the graph, the domain, we have all x values except the vertical asymptote, which is at x equals 0. So domain is x such that x is an element of the real numbers, but x cannot equal 0. For the range, this is a little different than we've seen before. Both of our curves are above the x-axis. Our horizontal asymptote is y equals 0. So we can't have anything equal to 0, and we also have nothing below 0, which means our range is y such that y is greater than 0 and y is an element of the real numbers. Looking at g of x next, the domain is everything except for the vertical asymptote, which is 3. So x such that x is an element of the real numbers, but x cannot equal 3. And for the range, both of our curves are below the x-axis, or the horizontal asymptote of y equals 0. So y is less than 0, and y is an element of the real numbers. And finally, for h of x, we have all x values except the vertical asymptote of -1, so x such that x is an element of the real numbers, but x cannot equal -1. And the range is y such that we have all y values greater than the horizontal asymptote of 2, so y is greater than 2, and y is an element of the real numbers. Given the graphs below, write the equation of each function in the form y equals a over x minus h plus k. We want to start by labeling the equations of the asymptotes. We have x equals to 2. We know that the vertical asymptote also tells us the h value. So that means that h equals 2. And then we have a horizontal asymptote at y equals 3, which tells us the k value is 3. We can plug those into our function y equals a over x minus h, which is 2, and then plus k, which is 3. Now we need to sub in a point for x and y so that we can solve for a. I can see 2 points on my graph. I have 1, 2, and then 3, 4. I can sub either of those in for x and y. I'm going to go with 1, 2. 2 equals a over 1 minus 2 plus 3. I'm going to solve for a now. Subtract 3, I get -1 equals a over 1 minus 2 is -1. Multiply both sides by -1. I get 1 is equal to a, and then I can plug it in. Y equals 1 over x minus 2 plus 3. There is my function. Same process for the next one. Start by writing the equations for your asymptotes. Our vertical asymptote is at x equals -2, which means h equals -2. Our horizontal asymptote is at y equals -4, which means k is -4. Sub those in to our equation. Y equals a over x minus -2, so x plus 2, and then minus 4. We need to sub in a point for x and y. I see 2 points here. I have -3, -5, or I have -1, -1. I'm going to sub in -1, -1. -1 equals A over -1 plus 2 minus 4. I'm going to add 4 to both sides. 3 equals A over -1 plus 2 is 1. So A equals 3. Then my equation of my function is y equals 3 over x plus 2 minus 4. Mary is producing a tourism booklet for a town in BC. She's comparing the cost of printing from 2 different companies. The first company charges a $50 setup fee and $2.50 per booklet. The second charges $80 for setup and $2.10 per booklet. Represent the average cost per booklet for each company as a function of the number of booklets printed. So average cost per booklet would be the total cost of the booklets divided by the number of booklets. So that total cost would be the setup fee plus the cost per booklet times the number of booklets and then all of that divided by the number of booklets. This would give us f of x equals, the first one is $50 setup fee plus $2.50 per booklet, so we'll call the booklets x, divided by the number of booklets again, which is x. Our second function to represent the other company, their setup fee is $80 plus $2.10 per booklet times the number of booklets divided by the number of booklets. So those are our two functions to represent the two different businesses. Graph the two functions in your calculator and sketch it below. Let's enter our two functions. So we have bracket 50 plus 2.5x close bracket divided by x, and then bracket 80 plus 2.1x close bracket divided by x. Enter, graph that. Thinking about the situation, we're talking about number of booklets and average cost per booklet. So we definitely want to be in quadrant 1, positive x and positive y. I'm going to change my x min to 0. My x max number of booklets, I'm going to guess maybe like 100. I'm going to change my scale to count by tens. I'm going to change my minimum for the y to be 0. The y value represents the average cost per booklet, so I'm going to say maybe $20. I mean, that seems high, but it's okay. So, and I'm going to leave my y scale as 1. I'm going to graph this, and here is what I get. So the blue line is our first function, and the red line is our second function. Let's sketch our graph here. Down here we have number of books, and on the y value we have average cost per book. Our blue one looks something like this, and our red one looks something like this. Let's find, we can see, look here, it looks like they intersect and the red one starts to be below the blue one. So let's try to find the intersection point. Second trace, number 5, my dots on my first curve, hit enter, dots on my second curve, hit enter again. I really don't know why it does that. Graph, second trace, Number 5 for the intersect. First curve. I am on my first curve. Hit enter. Second curve. I am on my second curve. Hit enter. Do I want to guess? No. Hit enter again. Okay, I don't know why it does that. So using my Casio calculator, I get x equals, we'll put it right here, x is 75 and y is 3.17. Hopefully your guys' calculators do not do whatever this one is doing on the iPad. So that tells us what information. What does the intersection mean? Well, this is number of booklets, and this is cost per booklet. So if they intersect at that point, it means when 75 booklets are printed, the cost is the same at both companies. And is $3.17 per booklet. So last part, which company should Mary choose? Well, it depends on if she's printing less than 75 booklets or more than 75 booklets. So if she is printing less than 75 booklets, then we would say to choose the first company, because that was the blue graph, which has a lower y value for x values lower than 75. And then if she is printing greater than 75 booklets, then the second company. Because after 75 booklets where they are the same, then the second company would start to cost less. So depending on the number of booklets she's going to be printing. That brings us to the end of chapter 9.1.